Hello everyone. Today we are going to look at the second part of section 4.2, and this part is on apparent weight. Now remember, in the first part we talked about weight and how weight and acceleration due to gravity are related to each other and how your weight can change when you go from one planet to another. So this time we're going to stay on the Earth, but we are going to look at how weight can change even if you're on the Earth. So our learning target today involves calculating the relationship between force and acceleration due to gravity. And our essential question is, how does our weight change when the acceleration changes? So let's do a little quick review here. Remember that weight is the effect of Earth's gravitational pull on a mass. And we've mostly looked at the weight of people, but it works for any kind of mass. Our weight formula, Fg, remember Fg, the force of gravity, is the same thing as weight, is equal to mass times acceleration due to gravity. And as long as you're on the Earth, the value of g is 9.8 meters per second squared. Okay, that should all be familiar to you. So here's our big idea that I really want you to remember. This is important. Weight can change, but mass remains constant. It's really, 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 really important that you remember the mass remains constant, because if you lose track of that, then all these problems kind of fall apart. So weight can change, that's the newtons. Mass remains constant, that's the kilograms. All right, so now I want you to imagine you're on a roller coaster. If you don't like riding roller coasters, there's a couple more examples. You can think about planes taking off or landing. You can think about elevators going up and down. Roller coasters tend to be really easy to think about. Okay, so imagine you're riding a roller coaster. What happens as you start at the bottom of the ride? All right, so here you are. Let's make this stand out a little bit more maybe. Here you are down here at the bottom of the ride, and the ride is going to take off and it's going to shoot you up this hill, right? Here you go, really fast up the hill. How do you feel when you're sitting in the roller coaster car? Well, you probably get pushed back against the back of the seat, and all of a sudden your body feels a lot heavier. So that's the first thing I want you to think about. When you're riding on a roller coaster, on the way up, you feel heavier. Maybe I should write feel heavier. You're not actually. Now, why do we feel heavier? Well, we feel heavier obviously because we're going against gravity, right? Gravity's trying to pull us back down. We're going up against gravity, and so we feel heavier. So we feel heavier because we're going opposite the force of gravity. Okay, now if we were to draw a free body diagram here, we would have, let's see, green's a different color. We would have the force of gravity that would want us to be going down, and the roller coaster would be accelerating us up. And so that line should be longer. We call it the force of the roller coaster. Okay, and so our net force would be up, our acceleration would be up, and we would feel heavier because we're going against where gravity wants to pull us. Okay, so that's the first thing. So we would be heavier if we're going up. All right, so now we've got to the top of the hill. Let's go back. Here we are at the top of the hill. Okay, we're going to go zoop over the hill, and we're going to start going down. And now, how do you feel? So at that moment where you're going over the top of the hill and you're starting to go down, you're accelerating down, your body kind of pulls against the seatbelt, and you kind of feel yourself kind of going up, but like if your seatbelt wasn't there, you would just kind of keep going. All right, and so that is the moment at which you feel lighter. So at the top of the roller coaster, we feel lighter. Why do we feel lighter? Because now we are going in the same direction as gravity is pulling us. So again, if we were to draw ourselves a free body diagram, we would have acceleration due, or we'd have, force of gravity going down. We'd have the force of the roller coaster going up. This time the force of the roller coaster is smaller. Our net force is down. Our acceleration is down, and we feel lighter. All right, so when we talk about this feeling of being heavier or being lighter, that's called apparent weight. So your mass hasn't changed, and overall, you're still the same person. But when you're going up against gravity, you feel heavier. When you're coming down with gravity, you feel lighter. All right, so our formula for apparent weight, that change in your weight as you accelerate, is going to look like this. Apparent weight, all right, so weight's still a force, so force apparent is equal to the mass times acceleration due to gravity, right? We can't ignore that, plus the acceleration of the roller coaster or the elevator or the airplane or whatever. So the extra acceleration, okay? And if we think about what our variables here stand for, where's my box? Oh, goodness gracious. Where's my box? There it is. Okay, so apparent, F apparent, is our apparent weight. All right, which is either going to be more or less than our actual weight. M still stands for mass, and this is in kilograms. Oh, I almost forgot. Newton's up here, right? It's still a force. G, as long as you're on the Earth, is going to be 9.8 meters per second squared. And all of our apparent weight problems are going to take place on the Earth. And then A is the extra acceleration of the roller coaster, or the elevator, or the airplane, or the, I don't know, ride the Disneyland that kind of shoots you way up, whatever that's called. I can't remember. Okay, so how do we use these? How do we do this? How do we use this formula? So let's go ahead, because I always feel better when I have the formulas right there in front of me. So we're going to have two formulas. We have a weight formula, right, for just our normal weight, Fg equals mg. And we have an apparent weight formula. I'm just going to write apparent, APP, is m times g plus a. Okay, so let's go ahead and see what we've got here. So we've got a person with a mass of 55 kilograms riding a roller coaster on the Earth. On the Earth is important, right, because it tells us the value of g. So then that says calculate the resting weight of the person. So I know the mass is 55 kilograms. I know I'm on the Earth, so G is 9.8 meters per second squared. My formula is Fg equals mg. So I'm going to have Fg equals 55 times 9.8. I should have given us a little bit more room to work here, shouldn't I? And that is going to give us 539 newtons. Okay. So this person just standing around, not on the roller coaster, is going to have a weight of 539 newtons. Okay, so now the person is going to get on the roller coaster. The roller coaster is going up, and the roller coaster has an acceleration of 0.45 meters per second squared. So first of all, is the person feeling heavier or lighter? Yep, since the roller coaster is going uphill, the person's going to feel heavier. What does that mean? That means that when I find the apparent weight, it should be more than my 539 newtons. Okay. So let's calculate the apparent weight. So the mass, remember mass remains constant, so my mass is still 55 kilograms because this is the same person. I know I'm still on the Earth, so I have acceleration due to gravity of 9.8 meters per second squared. And I have some extra acceleration from the the roller coaster of 0.45 meters per second squared. So here's my formula. Apparent weight is mass times acceleration due to gravity plus the extra acceleration. So this is going to be 55 times 9.8 plus 0.45. So if I add those together, I get 55 times 10.25. And when I multiply that, I get 564 newtons. Now remember we said this person's heavier, and so I need to think, 564, is that greater than the 539 I had up here? Yes, it is, and so I feel pretty good about that. All right, excellent. Let's do the next one. Roller coaster goes over the top of the hill. The apparent weight becomes 520 newtons. Okay, does the person feel heavier or lighter? Good. Since we've gone over the top and we're coming down now, the person feels lighter. And you can see that that's true because my apparent weight is now 520 newtons. So not only is it lighter than the 564 I figured out here, it's also lighter than the 539 I had up here for their resting weight. So 520 is a lot lighter. Okay, then it says calculate the acceleration of the person on the way down. So I have an apparent weight of 520 newtons. I still have a mass of 55 kilograms because the mass doesn't change. G is still 9.8 meters per second squared because we're still on the Earth. And this time I'm looking for the acceleration of the roller coaster. So here we go. Nope. Let's try again. Apparent weight is equal to mass times acceleration due to gravity plus the acceleration of the roller coaster. So I'm going to fill in my 520. Mass is still 55. I have 9.8 for my acceleration due to gravity, and this A is what I don't know. Okay, so there are a couple of different ways you could solve this. You could distribute the 55 if you want to. I am going to divide both sides by 55 because I think it's going to save me a step later on. It doesn't really matter, though. If you would rather distribute, then go right for it. This is going to give me 9.45 is equal to 9.8 plus A, right? Because this cancels. And then I'm going to subtract my 9.8 from both sides. And I've kind of run out of room, haven't I? Well, all right. And I'm going to end up with negative 0.35 is equal to A. So my acceleration is 0.35, oops, it's negative, meters per second squared. So how come the acceleration is negative? Well, in this problem, because I have called 9.8 positive this whole time, right, that would be, the acceleration would be opposite of the positive 9.8. So that's why it comes out to be negative. And the person feels lighter, weighs less. All right, so apparent weight. How are we going to define apparent weight? Apparent weight, let's get something that's going to contrast here. Orange. So apparent, well, no, I won't abbreviate. Apparent weight is a change in weight based on additional acceleration. Now, it doesn't actually have to be in an elevator or a roller coaster or an airplane. You could actually also experience this if you just were driving along and you slammed on the brakes really hard, right? You would still be tending to go forward. You'd have a change in your apparent weight, but it's more noticeable when you're in a roller coaster or something like that. So this can occur when a person's on a roller coaster, but also taking off or landing in a plane. You would feel heavier when you're taking off and lighter when you're landing. Or on an elevator, you would feel heavier going up in the elevator and lighter coming down in the elevator. All right, so now it's your turn. You have a person whose mass is 39 kilograms riding in an elevator. You are going to do the same things we did up above. Find the resting weight of the person. Okay, right, that's part A. Find the resting weight. You are going to find the acceleration on the way up and the apparent weight of the person on the way down. Okay, as always, if you have any questions, make sure you write them on the side there so you can remember to ask me in class next time. And hopefully you can now calculate the relationship between force and acceleration due to gravity, and you have an understanding of how weight changes when acceleration changes. Thanks so much. I'll see you next time.